All right, so we just talked previously about how it is unreasonable to use sinusoidal steady state analysis for a large range of frequencies. It makes sense if we want to only solve the circuit at a particular frequency and we want to determine, say, the magnitude and the phase of this output VO or Vout across the capacitor. At that particular frequency, we can use phasors, but for frequency response, where we're interested in looking at the entire range of frequencies and what is the magnitude and the phase at all kinds of different frequencies. We don't want to solve the circuit 100, 1,000, 10,000 times. We would rather use frequency response, which we have just kind of been motivating up to this point, and now I'm actually going to show you how to obtain the frequency response plots for a circuit, for in particular this RC circuit. So I already have the RC circuit drawn here in the phasor domain, and we've already obtained this transfer function previously. This is the voltage gain of this RC circuit. Of course, it's the output voltage over the input voltage, and we get 1 over 1 plus j omega RC. If you're not sure where that comes from, I did that in a previous video in this module, so please go back and check that out. And so just to start, there's a couple different ways that you can obtain the frequency response, but the first thing to remember is that we talked about complex numbers that have the form x plus jy. Of course, that's the rectangular form of a complex number. And if we have a number in this rectangular form, we can basically extract the magnitude of that number, which is x squared plus y squared. And we can call that r. And we can get the phase, which is the tan inverse of y over x in that case, and that gives us phi or theta, whatever you want to call it. And then we can represent the number as r angle theta, which is a phasor, right? It gives us the magnitude of the vector created by these coordinates in the xy, or the real being the x and y being the imaginary. If I have this point here, this would be x, this would be y, and this would be x plus jy. Well, we can also represent it by a vector which has some magnitude r and some angle phi, right? We talked about all this previously in module 1, so hopefully that's all clear. And so what I want you to recognize, this is all, kind of making the page look a little bit sloppy, but I'll leave it. What I want you to recognize is that right now this is not represented as a complex number normally is, right? We have the j in the denominator of this fraction. It looks kind of messy, but we can really easily convert it into something of this form, this x plus jy form. And how do we do that? Well, we can do that simply by multiplying the top and bottom by what's called the complex conjugate of the denominator. The complex conjugate is basically the same real part, but the opposite imaginary part, right? So in this case, we're keeping the 1 the same, but we're flipping the sign of the imaginary part. And we're going to multiply the top and the bottom by 1 minus j omega RC. And you'll see why we do that in a second. And so the numerator is just going to be 1 times 1 minus j omega RC. So over here, I'll just write V out over Vs is equal to 1 minus j omega RC. And then in the denominator, I basically have this polynomial expansion that I'm going to want to do, where I multiply the first two terms, which is 1 times 1. So that gives me 1. Then I have a 1 minus j omega RC. So I get a minus j omega RC. Then I get a plus j omega RC. And so that's why this is actually useful. It's because it gets rid of the j in the denominator and only leaves a j in the numerator. You see those terms are going to cancel. And then we have a minus j times a plus j times an omega RC squared. Well, negative j times plus j is basically negative j squared, which is equal to just the value 1, positive 1. So I can rewrite this final term as just omega RC squared. In case that's not clear, what I just did is I did minus j omega RC times plus j omega RC. The omega RC's obviously become omega RC squared, and then negative j times positive j is the same thing as negative j times j. J squared is negative 1, so this just becomes 1. Okay, so just in case that wasn't clear, I just wanted to clarify what I did there. And so, of course, these two terms are going to cancel, and I'm left with 1 minus j omega RC over 1 plus omega RC squared. Oops. And now I can write this in terms of a real part and an imaginary part in rectangular form like I have here, right? Okay, so let's see how we can do that. So I'd write V out over Vs is equal to 1 over 1 plus omega RC squared minus J times omega RC over 1 plus omega RC squared. And now I have my real part here. My J is here, and my imaginary part is here. Okay? And so now I have written this in terms of the real part and the imaginary part, and I have it represented as a complex number. Now that I have it represented as a complex number in rectangular, I can obtain the magnitude and the phase for this complex number. Okay? So I can go ahead and do that really quickly. I'm not sure how long this video has lasted. I probably should have checked, but I guess I'll just go through it pretty quick. So if I want to find the magnitude of a complex number, right, I take the square root of the real part, right? I'm looking up in the top right now. I take the square root of the real part squared plus the imaginary part squared. So for me, it's going to be that the magnitude of V out over Vs is going to be equal to the square root of the real part squared, right? So it's going to be 1 over 1 plus omega RC squared, and that whole thing is going to be squared, plus omega RC over 1 plus omega RC squared, that whole thing squared. Okay? If I do the math here, you'll see that the common denominators, 1 plus omega RC squared, squared. And so what I end up with is the square root of 1 plus omega RC squared over 1 plus omega RC squared squared. And the top, basically one of these cancels with one of these, and I am just left with the magnitude, which is the square root of 1 over 1 plus omega RC squared, which I can write in terms of frequency F hertz by just substituting omega equals 2 pi F. I could rewrite this as V out over Vs is equal to the square root of 1 over 1 plus 2 pi F RC squared. All right. Let me move all this up. I know this video has gotten long. I'll do the phase in the next video. Just wanted to get through that. But let me go ahead and put a box around this because this is very important right here. This and this really are both important. Basically, now what I'm looking at is I'm looking at the magnitude of the transfer function here. Right? We were talking previously about the magnitude of this signal. Right? I'm looking at this signal. This signal is the output voltage of my linear network. And I'm saying now what I have is I have an actual function for the magnitude here that's a function of the frequency, the resistance, and the capacitance in my circuit. The resistance and the capacitance, of course, that RC, we remember that to be tau. That's our time constant, right, for an RC circuit. So if I plug in a frequency value here for a given RC, I'm going to get some magnitude out. If I plug in a different frequency, I'm going to get a different magnitude out. And so that is what we were after, is a function that tells us the magnitude of our output, our transfer function for any given F, any given frequency that we could be interested in, okay? And so if we were to go ahead and plot that, I'm not going to plot it right now because this video really is getting long, but I'm saying I have frequency here, and I basically have the magnitude of V out over Vs here, and I can plug in any given number of frequency values, and I can get some kind of a response here to see what's going to happen to my magnitude as I vary the frequency of the input signal in my circuit. Okay, so I'm going to go ahead and end this video here. I know this one's gotten pretty long, but I think that this was an important video, so I didn't want to cut it short. In the next video, we'll go ahead and find the phase of this complex number that we discovered here, this one. And then once we have the magnitude and the phase, we can go ahead and plot our frequency response. Okay, so I'm gonna go ahead and end this video.